When we look up at the night sky, it's easy to believe that everything the sun touches somehow belongs to our solar system. For centuries, every comet and asteroid we saw was assumed to be one of ours, fragments from our own protoplanetary disk, bound to the sun by gravity and destined to return, again and again, in predictable paths. That picture quietly lived in astronomy textbooks for generations, and then, within less than a decade, it broke. In 2017, surveys scanning the sky for near-Earth objects picked up something that didn't fit the usual pattern. Its path around the sun wasn't an ellipse, like a comet or asteroid on a long, stretched-out orbit. It was a hyperbola, an open curve. Its eccentricity was greater than 1, and its incoming speed was too high for the sun to have captured and then gently kicked it back out. This was Oumuamua, the first confirmed interstellar object. It didn't just pass through our solar system, it came from somewhere else entirely, carried by the gravity of the Milky Way rather than bound to our star. Just 2 years later, in 2019, another visitor appeared, 2IR Borisov, discovered by an amateur astronomer in Crimea. Unlike Oumuamua, Borisov behaved more like a classical comet, with a bright fuzzy coma and a clear tail. But its orbit told the same story, hyperbolic, unbound, moving too fast to be native to the solar system. For the first time, astronomers could watch the ices and dust of another planetary system evaporate in real time as it swept past our sun. And then, in 2025, came a third surprise, 3IR Atlas. Detected by the Atlas survey in Hawaii, this object quickly revealed itself as another interstellar comet, again on a hyperbolic trajectory, again simply passing through. Images showed multiple tails and unusual structure in its coma. Spectroscopic observations suggested a chemistry that doesn't entirely match our local comets. 3 small icy bodies, 3 different stories, and all of them born under a different star. What makes these objects truly interstellar is not a label we chose, but the language of their orbits. A body that formed with the sun will, unless violently perturbed, move on a closed path, a nearly circular orbit like Earth's, or a stretched ellipse like a long-period comet. The key quantity is the orbit's eccentricity, e. If e is less than 1, the path is closed. If e is greater than 1, the path is open. For Oumuamua, Borisov, and Atlas, the eccentricity is comfortably above 1, and their excess speed far from the sun stays above the solar system's escape velocity. They arrive from interstellar space, curve past the sun once, and then fade back into the DAC, never to return. In practical terms, that means we are catching these objects mid-flight, like stones thrown across a vast cosmic ocean. They were probably born in distant planetary systems, in protoplanetary disks that once surrounded other stars. Over billions of years, gravitational encounters, with giant planets, passing stars, or even galactic tides, likely kicked them out of their home systems entirely. Now they drift through the Milky Way, mostly invisible, until chance brings one close enough for our telescopes to notice the faint, fast-moving point of light against the background stars. This episode will follow that story step by step. First, we'll define what an interstellar object really is, and why hyperbolic orbits with eccentricity greater than 1 are the smoking gun that proves an origin beyond the sun's gravitational family. Then we'll dive into the 3 known examples in detail. 1I Oumuamua, the first, and still the most puzzling, visitor, with its strange light curve and non-gravitational acceleration that can be explained by subtle outgassing, even if we never saw a classic comet tail. 2IR Borisov, the first interstellar object that truly looked and behaved like a normal comet, but with a chemical mix, especially in carbon monoxide, that hints at a much colder birth environment than typical solar system comets. 3IR Atlas, the newest member of the family, with its multiple tails, unusual colors, and hints of exotic chemistry, giving us fresh clues about how different other planetary systems can be. In the end, these 3 small bodies are more than curiosities. They are physical samples of other planetary systems delivered right into our cosmic front yard. Each one carries information about the temperature, composition, and dynamical history of its birthplace. By studying their orbits, brightness, spectra, and activity, we are starting to build a comparative atlas of planetary systems across the galaxy, not just by looking at distant stars, but by catching tiny fragments that have escaped them. This is the story of how we realize that the solar system is not closed, but porous, and that, every once in a while, the rest of the galaxy sends a messenger through our sky. When astronomers talk about visitors from another star, they are not being poetic. They are literally reading that story out of the orbit. Every body bound to the sun, planets, asteroids, most comets, follows a closed path described by the laws of celestial mechanics. The shape of that path is encoded in one key number, the orbital eccentricity, E for circular orbits, E is 0. Stretch that circle into an ellipse and E grows, but as long as it stays below 1, the object is gravitationally tied to the sun and will keep looping around forever, unless something kicks it. A special limiting case, with E exactly equal to 1, is a parabolic trajectory. The object arrives with just enough energy to escape the sun's gravity and drift away, never to return, but it could in principle have formed in our system and been flung out. Interstellar objects live beyond that boundary. Their orbits are hyperbolic, with eccentricities greater than 1, and that small-looking mathematical change carries a huge physical meaning. A hyperbolic orbit is not a loop but an open curve. It describes a one-time flyby. The object comes in from interstellar space, swings past the sun once, and then disappears back into the dark on a new course. To follow such a path, it must arrive already carrying more energy than the sun's gravity can bind. In other words, it was accelerated somewhere else, most likely in the gravitational fields of other stars and planets in a completely different planetary system. Astronomers quantify this extra energy in terms of hyperbolic excess speed, often written as V infinity, V infinity. Imagine turning off the sun's gravity and asking, how fast would this object be moving far away, out in deep space? For typical comets that were born in the outer Oort cloud and nudged inward by passing stars or the giant planets, this excess speed is effectively 0. Their orbits may be very stretched, with eccentricities extremely close to 1, but if you track them carefully, you find that they are still bound to the solar system. Any apparent value of E slightly above 1 is usually just measurement uncertainty or the result of small gravitational kicks during their passage. By contrast, true interstellar objects show well-measured eccentricities comfortably above 1 and non-zero hyperbolic excess speeds of tens of kilometers per second. That is far beyond what the combined gravitational tugs of the Sun, Jupiter, and the other planets can impart to a typical comet that started life in our own system. Their energy budget simply doesn't add up if you try to make them local. The only reasonable conclusion is that they formed around another star, were ejected, perhaps during the chaotic early stages of planet formation, and then wandered through the galaxy until, by coincidence, they crossed the tiny volume of space occupied by our planetary system. If interstellar objects are that clearly marked in their orbits, why have we only seen 3 so far, Oumuamua, Borisov, and Atlas? The answer lies in how hard they are to catch. These bodies are small, often only a few hundred meters or a few kilometers across. They are fast, racing through the inner solar system at relative speeds much higher than typical long-period comets. And most of the time they are dim, unless they are actively shedding gas and dust like a bright comet. They reflect very little sunlight and remain invisible to our telescopes until they are already close to the Sun or Earth. Surveys like Pan-STARRS, Atlas, and other wide-field sky scanners sweep huge patches of sky night after night. But even so, they are always racing against 3 things they cannot control: limited sensitivity, limited sky coverage, and the short time window during which an object is both bright enough and in the right part of the sky. That means the 3 confirmed interstellar visitors we know today are almost certainly just the visible fraction of a much larger unseen population. Most wanderers from other planetary systems pass through unnoticed, too faint, too far, too fast relative to our current instruments and survey strategies. As new surveys with more sensitive detectors and larger fields of view come online in the coming years, especially facilities dedicated to catching fast, transient objects, we expect the trickle of interstellar detections to grow. With every new hyperbolic track we map, we gain another tiny sample of the debris other stars throw away, a sparse, moving archive of how planets form and evolve across the galaxy. In October 2017, the Pan-STARRS survey in Hawaii picked up a faint, fast-moving point of light that did not behave like an ordinary asteroid or comet. Follow-up observations quickly showed something astonishing. This object was not bound to the Sun at all. Its orbit was strongly hyperbolic, with an eccentricity of about 1.2 and a significant excess velocity even far from the Sun, marking it as the first confirmed macroscopic body we have ever seen that came from another star system, crossed ours, and kept going. Its trajectory told the first half of the story. Oumuamua plunged into the inner solar system from above the plane of the planets, passed inside Earth's orbit, and was already on its way out when we noticed it. Because it was discovered so late in its passage, Astronomers had only a few weeks to gather as much data as possible before it faded beyond the reach of our largest telescopes. Even in that short window, it refused to behave like anything familiar. Photometrically, Oumuamua was strange. As it spun, its brightness changed by a factor of roughly 10, far larger than for most known asteroids. The simplest way to explain this is with a highly elongated or flattened shape, something like a cigar or a pancake with an aspect ratio perhaps between 5:1 and 10:1. On top of that, its rotation was not smooth. The light curve suggested tumbling, non-principal axis rotation, as if the object had been disturbed by a past collision or tidal interaction and had not yet relaxed into a stable spin. Instead of a neat, slowly turning rock, Oumuamua looked more like a battered shard, flipping and wobbling through space. Then came the real puzzle. Its motion did not match pure gravity. When astronomers fitted its path through the solar system, they found a small but statistically significant non-gravitational acceleration, directed roughly away from the Sun. For comets, this is normal. Jets of gas escaping from sun-warmed ice act like tiny thrusters. But Oumuamua showed no classical signs of cometary activity. No visible tail, no dust coma, and no clear detection of the usual volatile gases. It behaved dynamically like a very weak comet, but looked photometrically like a dark, inactive asteroid. This mismatch triggered a wave of hypotheses. One family of ideas suggested that Oumuamua was rich in exotic ices that could sublimate without leaving strong spectroscopic fingerprints or much dust. For example, molecular hydrogen or nitrogen ice from the surface of a Pluto-like body in another system. Others proposed that it might be extremely low-density fractal material, like a giant, fragile dust aggregate, so lightweight that even very small outgassing forces or radiation pressure could measurably alter its trajectory. More speculative papers played with the notion of an artificial origin, a light sail or engineered fragment, but there is no direct observational evidence requiring such explanations, and the consensus in the scientific community remains that Oumuamua is a natural object. What makes Oumuamua scientifically important is not just that it was weird, but that it was proof of concept. It showed that interstellar debris is not a theoretical background population, but a real, detectable component of our cosmic environment. It demonstrated that planet-forming processes in other systems can produce fragments very different from the asteroids and comets we are used to cataloging. And it highlighted the limitations of our current surveys. By the time we saw this visitor, it was already leaving. The natural next step is clear: to improve our sky coverage, find the next Oumuamua earlier, and, one day, be ready to send a spacecraft to meet such an object in person. When 2I Borisov first appeared in our skies in late 2019, it looked, at a glance, like just another faint, fuzzy comet, a condensed nucleus wrapped in a soft coma, trailing a thin tail of dust and gas. But its path through the solar system told a very different story. Its orbit was not a stretched ellipse like those of ordinary comets, but a steep hyperbola, with an eccentricity of about 3.36 and a large excess velocity even far from the Sun. That trajectory meant one thing: this object was not born here and would never return. It had fallen into our neighborhood from interstellar space, swung once around our star, and was already on its way back into the dark when we found it. 2I Borisov was discovered on the 30th of August, 2019 by Ukrainian amateur astronomer Gennady Borisov, using a custom-built 0.65-meter telescope in Crimea. Follow-up observations quickly refined its orbit and confirmed that its speed and path could not be explained by any gravitational scattering within the solar system. At perihelion it dived well inside the orbit of Mars, but its inbound velocity was too high for the Sun to have captured it and later flung it out. The numbers only made sense if it had started far outside the Sun's sphere of influence and was simply passing through. Almost immediately, the International Astronomical Union assigned it a new designation class, 2I, the second recognized interstellar object, following 1I Oumuamua. Unlike Oumuamua, which remained a point-like object with no clear signs of a coma, Borisov behaved in a way that felt comfortingly familiar to comet observers. Early images showed a condensed central condensation surrounded by a diffuse, symmetric coma and a faint dust tail aligned roughly opposite the Sun's. Spectroscopic observations revealed typical cometary emissions, cyanogen, CN, diatomic carbon, C, and later clear evidence of water vapor as the comet drew closer to the Sun and its ices began to sublimate. In terms of appearance alone, 2I Borisov could easily have been mistaken for a long-period comet from our own Oort cloud. But beneath that familiar look, The details of its chemistry told a more unusual story. Observations with the Atacama Large Millimeter Submillimeter Array, ALMA, and other facilities measured the relative abundances of gases in the coma, focusing especially on water, HO, and carbon monoxide, CO. In most solar system comets, CO is present, but usually at only a few percent of the water abundance, roughly on the order of 4%. In Borisov, the CO to HO ratio was far higher, in some analyses tens of percent and in others approaching or exceeding parity with water, depending on the epoch and method. That means that for every unit of water vapor coming off the nucleus, there was an unusually large amount of CO being released into space. Carbon monoxide is far more volatile than water. It condenses and remains stable only at very low temperatures in the outer regions of a protoplanetary disk. The high CO abundance in Borisov strongly suggests that it formed in a region of its home system that stayed extremely cold, colder, on average, than the regions where many solar system comets formed. It may have accumulated its ices in a distant belt analogous to, but even more frigid than, our Kuiper belt, where CO could be trapped efficiently in the nucleus. That makes Borisov a kind of chemical envoy from an outer disk we will never directly see, preserving in its interior the temperature and composition conditions of another star's far suburbs. At the same time, Borisov was not completely alien. Aside from its high CO content, much of its gas and dust looked broadly consistent with what we know from solar system comets: water ice, carbon-bearing molecules, silicate dust grains. Its dust colors and polarization properties were comparable to those of typical comets that occasionally visit our inner system. In that sense, Borisov reassured astronomers that the basic physics of comet formation, ice and dust aggregating in the cold outer disk, later scattered by giant planets and occasionally ejected into interstellar space, may be universal. The differences show up in the ratios and details, not in the fundamental ingredients. Because 2I Borisov was active and relatively bright for many months, telescopes around the world and in space were able to follow it through a long arc of its passage. Hubble Space Telescope images resolved the inner coma structure and tracked how the tail evolved as the comet approached and then receded from the Sun. High-resolution spectra tracked changing outgassing rates and hinted at how the surface layers of the nucleus responded to solar heating. In late 2019 and early 2020, observations even suggested that fragments may have broken off, indicating that the nucleus was likely fragile, consistent with a loosely bound rubble pile of ice and dust rather than a solid block. All of this extended time coverage gave astronomers a multi-month, multi-wavelength case study of an object assembled in an entirely different planetary system. Taken together, Borisov's story paints a nuanced picture. On one hand, its coma and tail behaved in ways that comet scientists understand well: sublimation, dust entrainment, radiation pressure shaping the tail. On the other hand, the extreme CO abundance and possible structural fragility mark it as chemically and physically distinct from most comets we know. It tells us that other stars not only form comet belts, but that those belts can have significantly different temperature histories, chemical gradients, and dynamical environments. Each interstellar comet we catch is effectively a core sample drilled out of a foreign protoplanetary disk and delivered straight to our instruments. Most importantly, 2I Borisov showed that interstellar visitors are not one-off curiosities. First we found a strange, mostly inert object, Oumuamua. Then we caught a much more typical comet that nevertheless carried an exotic chemical fingerprint. Now, with 3I Atlas and future discoveries from wide-field surveys like Vera C. Rubin Observatory's LSST, we stand at the beginning of a new observational field, comparative planetology between star systems, conducted not through exoplanet transits alone, but through the debris those systems throw into the dark. Borisov was our first clear look at a truly comet-like body from another star, and it confirmed that, while the language of planet formation may be universal, every planetary system speaks it with its own distinct accent. When astronomers first noticed a faint moving point on images from the Atlas telescope in Rio Hurtado, Chile, on the 1st of July, 2025, it looked like just another new comet. Only after its orbit was calculated did the picture change. This object was not simply paying the Sun a routine visit. Its path through space was hyperbolic, with more than enough energy to escape the solar system forever. It was officially named 3I Atlas, the third known interstellar visitor after 1I Oumuamua and 2I Borisov, and the first one discovered already in a clearly active cometary state. Unlike Oumuamua, 3I Atlas immediately behaved like a classic comet. As it fell toward the inner solar system, heating from sunlight woke up its ices. Observations with the Hubble Space Telescope in early August 2025 revealed a compact, bright coma, a cloud of dust and gas surrounding the nucleus, and the beginnings of a dust tail being pushed away from the Sun by radiation pressure. From a nearly star-like speck, the object transformed into a miniature, glowing atmosphere tens of thousands of kilometers across, behaving in many ways like the long-period comets that dive in from our own Oort cloud. As weeks passed and 3IO Atlas moved inward, larger observatories turned their attention to it. The James Webb Space Telescope captured the comet's spectrum in the infrared, separating its light into fingerprints of different molecules. Those data revealed a familiar but rich mixture: water vapor, carbon dioxide, carbon monoxide, carbonyl sulfide, and solid water ice grains streaming away from the nucleus. Chemically, this looks recognizably comet-like, the same basic ices that dominate many comets from our own system, but the precise ratios between them are still being measured. Those relative abundances will be the key to understanding how and where this object formed around another star. Dynamically, 3IO Atlas is extreme even by comet standards. Size estimates put its nucleus somewhere between a few hundred meters and a few kilometers across, modest on the scale of solar system comets, but its speed at closest approach to the Sun is extraordinary, roughly 250,000 kilometers per hour. That velocity is a fossil of its long exile in interstellar space. Over billions of years, weak gravitational nudges from passing stars and the galaxy's tidal field have reshaped its orbit, leaving it on a fast, unbound trajectory that simply cuts through the solar system and keeps going. Near the Sun it flared into activity. As it recedes, the outgassing will fade and it will return to being a dark, cold shard wandering between the stars. The geometry of its flyby is reassuringly distant. 3IO Atlas passed closest to Mars on the 3rd of October, 2025, at about 29 million kilometers, and reached perihelion, its minimum distance from the Sun, on the 29th of October, 2025 at around 203 million kilometers, just inside Mars's orbit. Its closest approach to Earth, on the 19th of December, 2025, is about 270 million kilometers, with the comet on the far side of the Sun at the time. That makes it scientifically fascinating but entirely harmless. It is not a near-Earth object and poses no impact risk. Planetary defense teams still track it carefully, both as practice in orbit determination and as a rare chance to test their tools on a foreign body moving at high speed. Because no spacecraft was anywhere near the right place or speed to intercept such a fast, short-notice visitor, all our knowledge of 3IO Atlas comes from remote sensing. ESA and NASA have coordinated a kind of solar system-wide observing campaign. Earth-orbiting space telescopes like Hubble and JWST watched from near our planet, while interplanetary probes, Mars Express, ExoMars TGO, JUICE, even SOHO, turned their instruments toward the comet whenever geometry allowed. Together, these perspectives at different distances and angles will be combined into a three-dimensional, time-evolving picture of how an interstellar comet behaves as it dives through a new planetary system's inner regions. Data from some of these spacecraft, especially JUICE, will arrive with delays of months, so the scientific story of 3IO Atlas will continue to unfold well after it has faded from the night sky. With 3 confirmed interstellar objects now on the books, patterns are beginning to emerge. Oumuamua was small, oddly shaped and apparently almost dust-free. Borisov was a more classical comet with unusually CO-rich ices. 3IO Atlas looks, so far, like another active comet with a familiar suite of volatiles but its own chemical nuances and dynamical history. Together, they hint at a galaxy filled with debris from countless planetary systems, each occasionally throwing out fragments that drift for eons before plunging through someone else's sky. Every such visitor gives us a direct sample, even if only in light, of conditions in disks and outer reservoirs around other stars. As survey telescopes grow more powerful in the coming years, we are likely to discover many more, turning these rare encounters into a new, statistical window on how planets and comets form across the Milky Way. In our own solar system, the story of planets did not end once the major worlds settled into their orbits. From the very beginning, the region around the young Sun was a crowded, chaotic place filled with countless planetesimals, icy and rocky bodies ranging from meter-sized boulders to objects hundreds of kilometers across. These small bodies were constantly pulled, nudged, and flung around by the growing planets. The same thing happens in other planetary systems. Wherever giant planets form, they become powerful gravitational engines that can reshape orbits, or eject objects entirely. In a young system, forming giant planets like Jupiter do not sit quietly. As they accrete gas and grow more massive, their gravity perturbs the orbits of nearby planetesimals. Some are scattered inward, some outward, and some are thrown onto highly elongated, eccentric paths that take them far from their star. Over millions of years, repeated close encounters with these giants act like a series of gravitational slingshots. Each encounter can either steal or give orbital energy. For a fraction of unlucky, or lucky, small bodies, the cumulative effect is enough to push their total energy above the escape threshold. At that moment, they are no longer bound to their home star. They become interstellar wanderers. Not every scattered object escapes immediately. Many are packed into distant, weakly bound reservoirs on the outskirts of their systems, analogues of our Oort cloud. These clouds are shells of icy bodies extending tens of thousands of astronomical units from their stars. They form when giant planets hurl comets outward, but not quite fast enough to unbind them. Over billions of years, passing stars and galactic tides can gently disturb these distant orbits. Some of these bodies fall back inward as long-period comets. Others receive just enough extra push to cross the final threshold and drift away into interstellar space. In that sense, the entire lifetime of a planetary system is accompanied by a slow leak of small bodies into the galaxy. The mechanisms that eject interstellar objects are well understood in principle. Numerical simulations of young planetary systems show that even a single Jupiter-mass planet can eject the majority of planetesimals it interacts with, especially if there are multiple giants or if the system undergoes orbital instabilities where planets themselves migrate or scatter. Over time, this process can expel an enormous mass in small bodies. Estimates suggest that a typical planetary system might eject the equivalent of tens of Earth masses in comets and asteroids into interstellar space. Scaled up to the hundreds of billions of stars in the Milky Way, the galaxy should contain an immense, diffuse population of rogue icy and rocky objects drifting between the stars. If the galaxy is filled with these fragments, why have we seen only 3 confirmed interstellar visitors so far: Oumuamua, Borisov, and Atlas? The answer lies in a combination of size, darkness, and geometry. Most ejected bodies are expected to be relatively small, kilometer scale or less, and made of dark, carbon-rich material. They do not shine by themselves. They only reflect the faint sunlight they receive when they pass through another system's planetary region. Unless one of these objects happens to pass very close to the Sun, it will remain too dim for our telescopes to detect. Even when it does pass close, it moves rapidly across the sky, spending only weeks to months in a brightness range where wide-field surveys can notice it and track its orbit accurately. Our current detection capabilities are also quite young. Dedicated all-sky survey systems like Pan-STARRS and Atlas have only been operating for a little over a decade. Before that, the sky simply was not monitored with sufficient depth and cadence to catch small, fast visitors from interstellar space. The fact that we have already discovered 3 such objects in this short time strongly suggests they are not rare. It is our observing time that has been short. As more sensitive surveys come online, such as the Vera C. Rubin Observatory's Legacy Survey of Space and Time, we expect the number of known interstellar objects to grow dramatically. Each new detection will add another data point to the emerging picture. Most interstellar visitors will likely be unremarkable, natural products of planet formation, yet together they will map the hidden traffic of debris that connects planetary systems across the galaxy. In this view, Oumuamua, Borisov, and Atlas are not isolated curiosities, but the first clearly recognized members of a vast, unseen population. They are the pieces that other planetary systems have thrown away, fragments of their own formation histories, now drifting through the Milky Way. When one of these fragments happens to intersect our tiny observational window, we get a brief chance to study foreign chemistry, foreign ice, and foreign rock. And behind each fleeting visitor lies a simple, powerful story. Wherever planets form, gravity both builds worlds and throws countless smaller ones out into the dark. Taken together, 1 Io Oumuamua, 2 Io Borisov, and 3 Io Atlas form the beginning of something like a small, imperfect catalogue of other planetary systems, not through telescopic images of distant disks, but through physical fragments that have actually flown through our own sky. Even with only 3 examples, a picture starts to emerge. Planetary systems across the galaxy are not just common, they are chemically and dynamically diverse in ways we are only starting to touch. Chemically, the contrast between these visitors is striking. Oumuamua behaved like no comet we know. Its orbit showed a tiny but measurable non-gravitational acceleration, as if gas jets were gently pushing it. yet telescopes failed to detect either a visible dust coma or the usual gaseous signatures seen in active comets. That combination led to ideas ranging from sublimating exotic ices, like molecular hydrogen or nitrogen, to an extremely porous, fluffy structure that could be pushed efficiently by outgassing or even by radiation pressure. None of these explanations is perfectly satisfying, but they all point in the same direction. At least some outer disks around other stars can produce bodies with compositions or internal structures that simply do not occur, or are very rare, in our own small sample solar system. Borisov, by contrast, looked like an archetypal comet the moment it appeared. A bright coma, a clear tail, classic cometary gases in its spectrum. But when astronomers began to dissect its light more carefully, they found that it, too, was no simple copy of our comets. Observations with large ground-based facilities in ALMA showed that its carbon monoxide, CO, abundance, relative to water, was dramatically higher than typical for solar system comets, in some analyses an order of magnitude or more above the usual values. That implies that Borisov formed in an extremely cold reservoir of its home system, where CO ice could remain stable and be locked into small bodies. It is chemically cousin-like to some of the most volatile-rich comets we know, but it pushes that chemistry to an extreme, suggesting its natal disk had a different temperature structure or irradiation history than the one that produced our Kuiper belt and Oort cloud. The emerging story of 3IR Atlas adds a third flavor. Here again we see a classic cometary appearance, coma, tail, activity under sunlight, but with hints of unusual detail. Reports of a bluish overall color and the presence of an antitail, a dust feature that, by geometry, appears to point toward the sun rather than away from it. That sort of morphology tells us the dust distribution and grain dynamics are subtle, controlled by a blend of particle size, ejection speeds, and solar radiation pressure. Early spectroscopic work suggests that its gas mixture may not match solar system norms exactly, though the picture is still evolving as more data are collected and analyzed. If Borisov showed us that interstellar comets can be familiar but chemically skewed, 3IR Atlas hints that the range of allowed chemistries and dust environments may be even broader than we thought. From a formation point of view, each of these objects is a tracer of a different region and history inside its home planetary system. A CO-rich comet like Borisov almost certainly condensed in a zone colder than the classical water-ice snow line, perhaps analogous to the farthest reaches of our Kuiper belt or even beyond. An object like Oumuamua, with its odd outgassing and inferred low density, might be a shard produced by violent processes closer in tidal disruption of a larger body near a giant planet or central star, or collisional grinding in a dynamically active inner belt before being ejected. 3IR Atlas, with its active coma and distinctive dust structures, could represent yet another reservoir, perhaps a region where ices and silicates mix in different proportions, or where long-term irradiation has processed the surface differently than in our system. In that sense, these three bodies are not just curiosities, they are physical samples from three different addresses in three different protoplanetary disks. For planetary science, this is extraordinarily valuable. Until recently, our models of planet formation and small body evolution were constrained almost entirely by one system, ours. We inferred the architecture of other systems from exoplanet statistics and disk images, but we had no direct pieces of their small body populations. Now, for the first time, we can compare. Do comets elsewhere carry similar mixes of volatiles? Are their dust grains similar in size and composition? Are extreme CO abundances common or rare? How often do disks produce fragile, highly porous fragments like those proposed for Oumuamua? With each new interstellar object, we get another data point that either aligns with or challenges our existing models. If, over time, most interstellar visitors look wildly different from our own comets and asteroids, it will suggest that our solar system is chemically unusual. If they cluster around a familiar range of compositions with only occasional outliers, it will support the idea that the physics and chemistry of planet formation are largely universal. In the long run, these visitors also shape how we think about the galaxy as an ecosystem. Every star system constantly ejects debris, comets nudged outward by giant planets, planetesimals scattered by migration, shards from collisions in belts. The three interstellar objects we have seen so far are almost certainly a tiny, bright subset of a vastly larger hidden population, drifting in the interstellar dark. As we build better sky surveys and, eventually, dedicated intercept missions, we will be able to turn these brief encounters into a systematic science, sampling the outskirts of many planetary systems without ever leaving our own. In that sense, Oumuamua, Borisov, and 3i Atlas are more than one-off stories. They are the first pages of a new atlas of worlds we will never orbit, but whose chemistry and history we can still read in passing. Today, every confirmed interstellar visitor begins its story the same way, as a faint, moving dot in a sea of stars. We do not see a detailed shape or a polished cinematic object crossing the sky. At first, we see only a pixel that shifts its position from image to image, just a little too fast and on just the wrong kind of trajectory to belong to the solar system. That is where discovery really starts, with sky surveys that repeatedly photograph huge swaths of the heavens, night after night, and with software and humans trained to notice the things that do not behave like everything else. Right now, most of our detections come from wide-field survey telescopes that scan the sky for near-Earth asteroids and other moving objects. Pan-STARRS in Hawaii, for example, uses large digital cameras to image large patches of sky multiple times per night. By subtracting images and looking for tiny points of light that shift from one frame to another, it can pick out moving bodies down to very faint magnitudes. That is how one-eye Oumuamua was first noticed in 2017, as a fast, dim point that did not follow a bound, elliptical orbit. The Atlas survey, which later discovered 3i Atlas, works in a similar way but focuses on all-sky coverage to find potentially hazardous asteroids. Its wide-field telescopes scan most of the visible sky several times per night, providing a safety net for anything that suddenly appears and moves. Even 2i Borisov, though discovered by an amateur observer with his own telescope, was quickly folded into this network. Once reported, professional facilities around the world locked on and monitored it continuously. In practice, the hunt for interstellar objects is a collaboration between automated software that flags unusual motion and a global community of observers who confirm, refine, and follow up those candidates in real time. The challenge is that the observational window is brutally short. Interstellar objects approach at high speed, sometimes tens of kilometers per second relative to the Sun, and they are small, typically only hundreds of meters or a few kilometers across. They brighten only when they come close to the Sun and to Earth, which means they may be detectable only for weeks or a few months. Before discovery, they are too faint. After closest approach, they fade quickly into the background again as they accelerate back into interstellar space. We often first notice them when they are already heading out, as happened with Oumuamua. That makes every hour of observation precious. Astronomers must race to gather as much positional, photometric, and spectroscopic data as possible before the object vanishes below the detection threshold of even our best telescopes. In a sense, we are trying to fully characterize an alien world while it sprints through our field of view. Because of these limitations, the next generation of sky surveys is crucial. The Vera C. Rubin Observatory in Chile, with its Legacy Survey of Space and Time (LSST), is being built specifically to push this frontier. Its 8.4-meter mirror and enormous wide-field camera will image almost the entire visible sky every few nights, to a depth far beyond current all-sky surveys. That means more faint moving objects will be caught earlier, and their paths can be tracked with far more precision. For interstellar visitors, this translates into several key advantages. We can detect them sooner on their inbound trajectory, giving more time for detailed observations. We can build better statistics on how many there are and how their orbits are distributed. And we can begin to see not just the rare, bright examples, but a fuller sample of the underlying population. Optimistic models suggest that with LSST-class capabilities, we might go from one interstellar object every several years to the possibility of seeing them often enough to talk about genuine population studies rather than a handful of anecdotes. With earlier detection comes a more daring dream, not just watching interstellar visitors from afar, but flying out to meet them. The idea of an interceptor mission is simple but ambitious. Instead of launching a spacecraft to a specific target years in advance, we place a probe in a flexible orbit, perhaps near the Sun or Earth L2 point, where it can wait. When surveys like LSST and other telescopes flag a new, scientifically exciting object on a favorable trajectory, the interceptor can be commanded to change course and race to intercept. ESA's Comet Interceptor mission is a real step in this direction. It is designed to wait in space and then divert toward a yet unknown pristine comet, possibly even an interstellar one, releasing multiple probes to fly through the surrounding gas and dust and observe from several angles at once. In the longer term, similar concepts could be adapted specifically for interstellar visitors, with more powerful propulsion and dedicated sampling hardware. The ultimate goal would be astonishing: to bring back dust or ice grains that formed around another star, allowing us to study their chemistry in laboratories on Earth. Together, these developments transform interstellar visitors from occasional curiosities into a new branch of planetary science. Current surveys give us fleeting glimpses. Future observatories like Rubin will provide early warning and statistical power. Interceptor missions promise, one day, to turn those distant, fast-moving points of light into directly sampled material from alien planetary systems. Each step brings us closer to turning "we saw something strange fly by once" into "we understand how other planetary systems build and eject their small bodies," and perhaps into "we are holding a physical piece of another star's outskirts in our hands." When you step back and look at one Io Oumuamua, two Io Borisov, and three Io Atlas together, it becomes clear that these are not random specks that happen to wander through our telescopes. They are fragments of distant planetary systems, small enough to be overlooked by their home stars, yet significant enough to carry pieces of those systems' histories all the way to us. For most of human history, every comet and asteroid we saw belonged, in some way, to the Sun. Now we know that, every so often, something from someone else's sky passes briefly through ours. Oumuamua was the first and remains the most puzzling of these visitors. Detected in 2017 on a strongly hyperbolic path, it was clearly unbound to the Sun. It showed no obvious coma, looked more asteroid-like than comet-like, and its brightness varied in a way that implied a highly elongated or flattened shape. On top of that, precise tracking revealed a tiny non-gravitational acceleration, usually a sign of gas jets, even though we saw no clear gas or dust. The best current picture is that Oumuamua is a small, natural fragment of ice-rich material from another system, with a composition or structure that produces very subtle outgassing. It taught us that interstellar debris can be small, dark, strangely shaped, and hard to fit into the neat categories we built from our own solar system. Borisov, by contrast, felt almost familiar. From the moment it was discovered in 2019, it behaved like a classic comet, clear coma, tail, and months of sustained activity as it approached and receded from the Sun's spectroscopy showed the usual cometary gases and dust, but with strikingly high levels of carbon monoxide relative to water ice. That points to formation in an extremely cold region of its home system, where CO could freeze and stay locked in. Borisov reassured astronomers that the basic physics of comet formation seems universal: ice, dust, and weak gravity at the edges of planetary systems, but also reminded us that each system writes its own chemical accent into those ices. 3IR Atlas adds a third, still unfolding chapter. It follows a clearly hyperbolic path and shows a coma and tail more like Borisov than Oumuamua. Early observations hint at a distinctive appearance, reports of a bluish tone and unusual dust structures such as an antitail, along with possible differences in gas composition that are still being analyzed. Where Oumuamua showed us something we did not expect and Borisov showed us something we mostly did, 3IR Atlas is beginning to map out the space in between, familiar comet physics, but with new twists in color, morphology, and chemistry that expand the range of what normal can mean for interstellar comets. Taken together, these three objects reshape how we think about small bodies in the galaxy. They confirm that other planetary systems routinely eject comets and asteroids into interstellar space, just as ours does. They demonstrate that the diversity of those bodies, shapes, densities, ice mixtures, and dust is at least as wide as what we see near the Sun, and probably much wider. And they show that, even without sending spacecraft to other stars, we can still receive physical messages from those distant environments, pieces of foreign protoplanetary disks, passing briefly through our observational reach. The most important lesson may be how early we still are in this story. With only 3 confirmed objects, we are at the first data points on the graph stage. Future wide-field surveys will likely raise that number dramatically, turning rare surprises into a steady stream of detections. Concept missions designed to intercept a newly discovered visitor could one day fly close enough to sample material directly from another system. For now, though, these first interstellar visitors have already done something profound. They have turned our solar system from an isolated stage into a crossroads. Tiny, silent, and moving too fast to stay, they remind us that the galaxy is not just full of stars and planets, but also of countless small messengers, each carrying a story from a sun we will never see up close, but whose debris has come to meet us.